Let's do a problem involving Gauss's law and a slab. So here we have an infinite slab, and I've used the double arrows here at several points to show that this slab goes on and on in every direction except the vertical direction. But of course, I can't show that on a drawing very easily, so that's what that is supposed to mean. And there's a uniformly distributed positive charge throughout its volume. The volume charge density is rho, and the slab has a finite thickness of 2h. Point O lies within the centermost slice of the slab. In other words, it's equidistant, a distance h from both the top and bottom surfaces. And we want to figure out what's the magnitude of the electric field within the slab, that is when y is less than h, and then outside of the slab. And then we're going to graph our results. First off, how do we know that this slab is not a conductor? It's got to be an insulator. And how do we know that? Well, you can't have a uniformly distributed charge throughout the volume of a conductor. Anytime you have a conductor in electrostatic equilibrium, all the charge would necessarily be at the surface. And we're told that's not what we have here. This must be some sort of insulating material. All right, now from symmetry arguments, the magnitude of the electric field at point O, and in fact all throughout this centermost slice, has to be 0. If you put a test charge at point O, it will be repelled downward by charge up top, but it'll be repelled upward equally with charge that's below it. So the net electric field throughout the entire centermost slice has to be 0. Let's derive expressions for the electric field, and then we're going to graph the results. We've always used Gauss's law whenever we want to find an expression for the electric field. So first we're going to take the case where y is less than h. I'm going to draw here right there. Here's a little Gaussian cylinder right there. The top surface is not yet out of the slab, and that height right there is y. And let's call the area of this top here, let's call that A. We could make it a rectangular solid if we wanted, but I'm making it a cylinder here. It doesn't make any difference. Let's use Gauss's law, which says what? The enclosed charge over epsilon naught is equal to this quantity. What's the charge that is enclosed here? The charge that's inside here is the charge per volume multiplied by the volume of that little thing that looks like a hockey puck. And what is the volume of that? Well, it's the area multiplied by y. That's the volume. Charge per volume multiplied by volume will give you charge. There are no electric field lines on the bottom surface because remember, there's no electric field at that point, and there are no electric field lines on the lateral edges of this cylinder because the field lines just scrape those surfaces. So the only area that we're dealing with is the top surface here. The electric field is equal there everywhere. Then we would have to integrate dA, and when you do that, you just get A. So this is actually going to be pretty easy, isn't it? The A's cancel. That A cancels that A right there, and therefore the electric field, as we go nearer and nearer the surface, is going to be equal to rho times y divided by epsilon naught. Now, what about when we get outside the surface? Let's take the cylinder, and it's all the way out here now. Still got the same shape. Now my y extends all the way there above the slab. So now, for y greater than h, let's do something similar. The charge that's enclosed divided by epsilon naught is equal to the integral of E dot dA. What's the charge that's enclosed now? Well, the charge that's enclosed goes all the way up to the point of y equal h right there. But then there's no more. So the charge that's enclosed is rho, the charge per volume, multiplied by the volume of that plug right there, which is the area multiplied by h. The electric field has an equal strength everywhere. And again, that area is A right there. That's the only area we have to take into account. because, as we said just a little bit ago, the field lines only scrape the lateral surface. The field lines go pointing straight up here, so they don't pierce the lateral surface, they only pierce this top area, which means when we integrate dA, we get that area A. Once again, the area cancels out, and now the electric field is equal to what? Rho times H over epsilon naught. This is for an infinite slab. So if we graph these, what would that look like? We would graph the electric field on the vertical axis. We would graph Y on the horizontal axis. There's a value of Y equals H right there. And according to this, it looks like the electric field increases linearly up to Y equals H. And then it doesn't depend on Y at all. It's constant right there. For this portion, the electric field is a constant. And for this portion right here, the electric field is proportional to Y.